Section 3.4 is addition and subtraction algorithms, and then mental estimation, but we won't get to that part today. Algorithm just means a way of doing something, a method or process for how to do something, okay? So we're going to counter several ways of doing things. Some of them you've undoubtedly seen before, and some of them maybe you haven't. So the first one we're going to start with is taking 34 plus 18, and we'll use this example several times in different strategies and different algorithms. So the first algorithm is the concrete model. So this would be what you would be using when you're very first teaching addition and subtraction. And what you're doing is you're going to be drawing pictures, because whenever we hear the word concrete, it usually means pictures are involved. All right, so when we see 34, we've talked about base 10 blocks before, right? I brought in some base 10 blocks. Well, that's what we're going to be drawing. We're going to be drawing base 10 blocks for the number 34. So this would be 3 longs. And it would be 4 units. Okay, that's 34. And you're going to combine that with 18, which is 1 long and 8 units. And what our goal is our goal is to combine things that can be combined to simplify the expression we see. Kind of like when we were dealing with some of the questions in the last section or 2 sections ago with money, right? We want as few coins as possible. We want as few blocks as possible. So we can combine some of these little blocks. How many of these little blocks would we need to combine in order to make a long? Yeah, 10 of them. So here are 8 of them, and we need, 2 more. So here's 10 of these. And we're going to end up then with how many longs? 5. All my longs should be the same size. They're definitely not on my screen, but just pretend. And then how many units do I still have left? 2. So in a very concrete way, we can see that the answer is 52. Everybody good with that? Okay, so this is for preschool, kindergarten age kiddos for the most part, maybe first grade if you have some of the kids who are a little bit further behind than others, or that need a concrete visual for what's happening. The other place that you might see this being used is in first grade towards second grade, when they're starting to use the idea of carrying numbers, because that's what the standard algorithm does. So when we do 34 plus 18 in the standard algorithm just means the standard way that you probably learned to do addition. Do we start on the right-hand side or the left-hand side? The right-hand side, and we would add 8 plus 4, which gives me 12. And what we do is we write down a 2 and we carry a 1. Do you know why we carry a 1? It's a 10. And this concrete model gives a very good visual for what's happening when we're actually doing that. We're collecting 10 of these little units together, and we're turning it into a long. And that's what's actually happening when we carry the 1. And then we have 1 plus 3 plus 1, which gives me 5. One of the sort of drawbacks to this that you might not have considered before is that moving from right to left is counterintuitive for children. Why? Because we read from left to right. And so this can be a little bit tricky for a child first looking at it, because it just doesn't work the same way that they've been working with reading. Okay? All right. We'll talk about the expanded algorithm next. So the expanded algorithm is kind of an in-between of the concrete and the standard. So what we're going to do is we're going to take the number 34 and we're going to write it out as 3 times 10 plus 4 times 1. Okay, so we're writing it out as a base 10 expanded form kind of number. And then we do the same thing with the 18. We have 1 times 10 plus 8 times 1. And in this order, it actually doesn't matter if we go from left to right. So we could actually do 3 plus 1, so this is 4 times 10. We can do 4 plus 8, which is 12 times 1. Okay? Now we're not done yet, so have no fear. I'm not stopping the problem. But we can actually do that, and that kind of alleviates some of our left to right issues. The next thing that we have to recognize is that 12 times 1 is a 2-digit number. And so we kind of break the 12 times 1 down into 1 times 10 plus 2 times 1. And we already still had the 4 times 10 here, right? So we have 4 tens, we have 1 10, that's 5 tens. This is 5 times 10 now. Plus, and then we have our 2 times 1. And of course the answer then, looking at it in that form, because they both have single digit numbers times the powers of 10, is 52. Kind of an in-between step between those last two algorithms. Okay, but there's legitimately a left to right algorithm coming up next, and it helps if we've got a few more digits, so that's why I'm showing you this with a few more digits. So this is 1,534 plus 3,218. Okay, so what we're really going to do is we're going to add the 1 and the 3 together, and that's going to give me a 4, because what we're really adding is not 1 and 3. What are we really adding? 1,000 and 3,000. So the answer I'm going to write down right now is 4,000. And over here to the side, I'm going to write down what we really did, because that's what you told me to do, is 1,000 plus 3,000. So that's where the 4,000 came from. So a child could write that down, or they could just understand that fact. The writing down of what I just put in parentheses is not really part of the process. It's more part of the thinking behind it. And we're going to do the same thing with the 5 and the 2, but the 5 and the 2 really represent 500 and 200, which is 700, right? We have the 3 and the 1. Oops, I didn't write it right. Which is really 30 and 10, which is 40, right? And then we have the 4 and the 8. Those actually are 4 and 8. And 4 and 8 are 12 when they're summed together. We can still do this from left to right even now, right? So this is 4,752. And I didn't really mean to say and. That's not a correct statement. 4,752. Okay? So that's left to right. A drawback, of course, is that it takes a little longer. It's not terribly efficient. It's effective. It works. It's got this left to right business moving around with it that feels comfortable, but it is not terribly efficient.
I feel like it's a good way to explain them that the 1 and 3 really are 1,000,
Yes.
3,000 to actually understand. I know my nephew's having trouble right now mixing up carrying and borrowing, because
Yeah.
when you carry, it's a 10 now, and so you add it like that, but when you borrow and you carry it over, it's like 12, you know?
Yeah.
And so he'll try to add 12 to the next to the left column. So I feel like
Gotcha.
this is I don't know, explains what you're actually doing with it. Just
Yeah, and I think that a lot of times the standard algorithm in and of itself hides a lot of what we're doing. And it does so because it is terribly efficient. It's a very efficient algorithm, which is why it's been used for so long and why it's the one you learned. It's because it was very efficient. But it hides a lot of the mathematics of what's going on behind it in sort of the background. And some of these methods, although they aren't terribly efficient, are very good at explaining what's happening. And so I like that one for what you just said as well. All right, what's our next one? Oh, okay, lattice algorithm. We're going to encounter a lattice algorithm right now for addition. We're going to also encounter one next week after we get back from spring break for multiplication. Lattice algorithm is my daughter's favorite. So my 11-year-old, when she uses standard algorithm now, and it's no problem, but she really struggled in particular with the multiplication in the standard algorithm. But when I explained it to her with the lattice algorithm, it all clicked. It was easy and it made sense. She loved it. Okay, so here's what you do. You're going to write down just like you did with the standard algorithm, or even left to right, 1894, 3218, okay? Underneath the numbers, you're going to write a long box, and because you're working with 4-digit numbers, you're going to split this into 4 small boxes underneath. That was not good. Okay, so the idea is that it's lining it up underneath the 4 numbers. Mine don't really appear to be very well lined up, but yours are probably better. Okay, the next thing that you do is you split the boxes along a diagonal, okay? And that's why it's called a lattice. It's because it looks like a lattice image. So here's what you do. Each of those boxes, you can move left to right, right to left, makes absolutely, you could work from the middle out. It doesn't matter. Each of the boxes are independent of the others. So I'm just going to work from left to right because, again, it has that nice natural feel to it that reading does. So 1 plus 3 is 4. We're going to write the 4 underneath in the box, but it's in the bottom right-hand corner. Okay? 8 plus 2 is actually 10, and so we're going to write the 1 in the top corner and the 0 in the bottom corner. Okay, so the top corner is the tens digit, the bottom corner is the ones digit for any of our addition. 9 plus 1 also 10, so top is a 1, bottom is a 0, and then 4 plus 8 is 12, so top is a 1, bottom's a 2. Everybody good so far? All right. The next thing you're going to do is you're going to add along the diagonals. And again, for the most part, it doesn't actually matter whether you move right to left, but occasionally it will. So we're going to start on the right-hand side, just in case it did. So this is a 2, right? Because there's nothing to add to it. But then I have 1 and 0, that's 1. 1 and 0 is 1, and 1 and 4 is 5. This is 5,112. One of the things it does by splitting it up is instead of actually carrying the one over to the next column, it does that, you just don't see it doing that, right? Because it's putting it in that top corner of that box. So what happens is, let's just take the 8 and the 4 one for example. So I get a 1 here and 2 here. This 1 is now in the tens column, which is exactly where this 0 right here is. It's the tens column. But this one actually ended up being 10, but this 1 was in the hundreds column. So now this is the hundreds column. It's just the columns run diagonals. So this is the lattice method. Okay, the next one is probably my favorite. It is not useful in general for everything. Okay, the scratch model, you can write down next to it, is practical when you're adding many numbers together. And really many numbers, means like 4 or more. Okay, so if you're doing fewer than 4, it doesn't really make a lot of sense. But it's very practical when you're adding a list of numbers together. So I'm going to write it exactly, like you would have written it with the standard algorithm and so forth, where we're sort of doing it vertically. All right, so let me sort of talk about the problem that you encounter when you do the standard algorithm here. If you're doing the standard algorithm, you're going to do 4 plus 8, and you're going to get 12. Then you're going to do 12 plus 9, which may or may not be in a student's sort of memorization of addition facts, right? So at some point, they're probably counting on their hands or something like that, or counting dots on the numbers, and, or something like this. Then, even if they did know that one, then they get 21, and 21 plus 7 is definitely not in their list of values. And while, yes, they should realize that 21 plus 7 is just add the 1 and the 7 together, that's not usually how students will think about it. They will add up in some way. Okay, so the problem in general with long lists of numbers is that we encounter values that are not values we've memorized. Do you guys agree? Make sense? Okay, so this one keeps them from actually having to do that. So here's what we do. Start at the top, 4 plus 8. What's 4 plus 8? 12. Okay, so anytime we get a number that's a 2-digit number, we're going to mark a scratch on the sheet, okay? And what we're going to do is we are going to ignore the tens digit and only remember the ones digit. So the number 12 is 1 10 and 2 ones, right? So we're going to ignore the 10 and we're going to remember the 2 ones. So in your mind, I want you to think, now I have the number 2. 2 plus 9 is 11. That's, again, too big, right? It's a 2-digit number, so we're going to scratch. Ignore the tens digit, remember the ones digit. The ones digit is a 1, and then you're going to add 1 plus 7, which is 8. So once we get to the 8, we're going to write the 8 down underneath. Every scratch, we ignored a tens digit, correct? So how many tens digits did we ignore? 2. That's the number we carry. And the benefit to having done so is that we were able, every time we added, to make use of the facts that we had memorized from single-digit multiplication. That's what we're able to do by ignoring the tens digit. And then we count up the tens digit when we're done, and we carry it over. So let's practice it again. 2 plus 3 is 5, so that's good. 5 plus 1 is 6, also good. 6 plus 6 is 12. That's too big. So we're going to scratch and remember the 2. 2 plus 8 is 10, which is actually as well too big. So we're going to scratch and remember 0. Very good. And so you're going to write the 0 down. Okay. How many scratches did you make? 2. So we're going to carry a 2 over to the next column. And I realize there's nothing in the next column. That's okay. That just means that I have a 2 that I carry straight down. So it's 208. It's an organized way of forgetting the things that make the problem difficult. That's what it really is. Okay, and the longer the list, the more practical this becomes. Okay. That's all of the addition algorithms. You ready to try some subtraction ones? Okay, the first subtraction ones are going to feel like, oh my goodness, we just did this already. Okay. First one, concrete model. We already drew these pictures, but we're going to draw it again. Draw me a picture for 34. So 3 longs and 4 units. Okay, the units should look like they're the same size as well. They're not quite perfect, but you got the idea. 34. All right, so one of the ways that we talked about subtraction is the idea of removing or taking something away. So if I were to take something away here, what does this say in terms of these blocks that I need to take away? 1 long and 8 units. And I've got a problem, right? I don't have 8 units. So what would you suggest I do visually so that I do have 8 units? Yeah, I need to turn a long into 10 units. So this is equivalent to now having the 2 longs and 10 units. I'll try that again. Okay, I don't mean 10 units, actually it's 14, right? Okay, I think I've got 14 of them, do I? I think so. Okay, this is the same value, it's just expressed differently. You can also think another concrete model, it's not the one that your book is using, is money, right? If you were to actually use, say, dimes and pennies would be a good example. So you have 3 dimes and 4 pennies, and you want to take away 1 dime and 8 pennies. What do you have to do? We have to turn a dime into a penny, right? You could do a visual argument with this as well. So now I actually have the ability to remove one of my longs, and I'll just draw an arrow indicating that I'm removing, or you can put a big old X on top of it. That'll be fine. You're removing it. And then I need to remove how many of my units? 8. So I'm going to try and find 8 of them. We'll do the first 8 right here. All of those are getting removed. So the answer after I remove these is what? 1 long and 6 units, which is the value 16. Okay, standard algorithm, you guys know how to do that. How do I do 34 minus 18 in the standard algorithm? What's that? Yes, we're going to have to subtract like the 4 minus the 8, and we run into a problem, right, Hannah? What's the problem?
We don't have enough to subtract the 8.
Exactly, we don't have enough. So what is it in subtraction that we do so that we get enough? We borrow, we take away a 10. So from the 10's place, we turn this 3 into a 2, and we turn the 4 into a 14. And that looks a little bit funny for a couple of reasons. Number one, it looks like we're taking something away and we have more than what we had before, which is a little weird. And we also have this sort of weirdness that there's a 14 now in one place, a 1 digits kind of place, which is a little awkward. But again, the concrete model explains why that happens, right? We took away one of the longs and we turned it into 10 singles, and we already had 4 singles to start with, 4 units to start with. So the concrete model gives the background, the explanation for why that's working for us. And then we can subtract. So 14 minus 8 is 6, and 2 minus 1 is 1. Okay. Expanded algorithm. We've done an expanded algorithm with addition. Works the same way with subtraction. You have 3 times 10 plus 4 times 1 minus 1 times 10. And it's also, you could say, minus 8 times 1. We're subtracting both components of that. And of course, you run into the exact same problem, right? I can't take away 8 from 4, okay? So what do I have to do? Well, I have to borrow. So I'm going to take away 1 from here, and I'll kind of shortcut my writing on it a little bit more shortcutted than I did before. And I'm borrowing that one of those 10s, and one of those 10s is equal to 10 of my 1s, and I already have 4 1s, so that gives me 10 plus 4 is 14. And then I can subtract. So 14 minus 8 is 6 times 1. And 2 minus 1 is 1 times the 10. So my resulting value is 16. All right. There's no lattice method. There's no scratch subtraction method. But there is something called equal additions. I know it sounds funny to even call it equal additions because, hey, we're subtracting. So let's see how this works. All right, I need you to write a statement down, big and bold, remind yourself. The point of equal additions is that we never borrow. That's the point. So if you get halfway through the problem and you find yourself borrowing, you're making a mistake. Okay? Equal additions, the point is that we do not borrow. So how does that work? Well, as you can see, I've got some larger numbers to deal with so you can see how it's actually working a little bit more fully. If I were doing this problem with the standard algorithm, I have that 4 minus 8 like I had on the last two problems, right? I don't do that. I don't have the ability to borrow if I'm using this method. So what do? Well, our goal is to turn the number on the bottom into something with a bunch of zeros. I mean, that's really the goal. We want this numbers to have zeros. If we can't subtract as is, we want to turn them into zeros, okay? So what would I have to add to 8 to turn it basically into something that has a 0 in that place value? 2. Now, if we add a 2 here, balance-wise, we have to equally, right, equal additions, add a 2 on top. And if I do that, I now have 836 minus 160. And so the ones column, no more needing to borrow. Agreed? But the tens column still needs borrowing, right? I can't do 3 minus 6 without borrowing. So what would I need to add to 6 to turn it into a 0? 4. And it would be 40 because I'm in the tens place. Exactly. So I'm going to add 40 to my 160. But if I add 40 to the 160, I also have to add 40 to the 836. Okay? So what is 836 plus 40? 876. And what is 160 plus 40? 200. So obviously I can subtract in the ones column, I can subtract in the tens column, and we're good to go in the hundreds column, right? So this is when we actually get to do the subtraction. And at this point, it doesn't matter if I move left to right or right to left because there is no borrowing, right? So this is 676. You know, it depends on how far you take this down the road, right? I mean, how far do we actually continue through the process? I will tell you that a lot of times when I have to subtract 9, I don't subtract 9s. I subtract a 10 and I add a 1 back in. I'm doing equal additions. I do it with 8s and 9s. I never subtract 8s and 9s from things. They're large numbers. Why would I do that? I always subtract the number that's close to a 10, basically like this, and then I make up for the fact that I didn't actually subtract the 8 or the 9. And so the more small scale this problem is, the easier it is to explain in this way. But the point of the process is, yes, to avoid the borrowing process itself. Every method, though, it has its pros and cons. One of the things that I want you to understand is that we talk about lots of ways to do things in class for a couple of reasons. Number one, you don't know what your books that you use are going to tell kids to be doing. And it's very disconcerting to be sort of slapped upside the face the first time you look at a book and you're like, this is not anything I've ever seen before. It makes you feel a little uncomfortable, right? So I don't want you to encounter things, at least on a regular basis, that you've never seen before. And then also, this method maybe isn't good for every kid, but there may be that one kid in the class that just gravitates towards this. And because you know this method and can use this method, they are able to do the problems in a way that works for them. Okay? Any other questions about this one? Okay. All right, we're going to do 2 more problems and we're going to call it quits for today, okay? I know you guys don't like other bases. We're not going to convert in and out of it anymore. Okay, you already did that. But what we are going to do is we're going to work in the other bases. So part of the reason why we're doing this is because you guys are very well versed in how to add and subtract. And so in some regards, it's really hard for you to think about why this is so hard. You've been doing addition and subtraction for a long time, right? So if we change the base on you, it puts your thinking hat back on and makes you sort of struggle a little bit like maybe your kids will struggle. So it kind of gives you that empathy, kind of gives you that sort of sense of what it is that makes it so difficult for the kids in base 10, because this is now a base that you're less familiar with than the base 10 that you have grown to love, okay? That's the idea. So we're going to do a couple of examples in base 8. And then we'll continue next time with some base 3 and some others. Base 8. Remember, base 8 has 8 numerals from 0 to 7, okay? So you can't add something together and get a 9 or an 8 in base 8. We're going to take a look at the numbers 3, 4 base 8 and 1, 7 base 8 and figure out what we would do if we were working in base 8 to add these numbers. And as we do the problem, what I'm going to do is I'm going to do the problem in 2 ways for you. The standard algorithm, we'll do it that way, okay, because I know that you feel comfortable with that one, and by and large you will be using that one in the classroom. But I'm going to also show you what it would look like in another base or another method to do it, okay? So in standard algorithm, we start on the right-hand column, 4 plus 7. 4 plus 7 in our number system is the number 11. Okay, so we want to think about when we look at the number 11, what is that in base 8? What is 11 in base 8? Well, the question really is how many 8s are in 11? 1 8. And how many are left over? What was it? 3. So we're going to carry 1 8 over, just like we carry over a 10, right? This is the 8s column now. What used to be our 10s column is our 8s column. So we're carrying over an 8, and we have 3 left over that we're going to write down underneath. And then 1 plus 3 plus 1 is 5, and that works in base 8, so we're done. 5, 3, base 8. Please make sure that you write the subscripts just like before, base 8. Good, I'm glad to hear that. Okay, so let's do the scratch addition method, because that's the other one I have written down apparently for this one to show you. 3, 4 plus 1, 7 in base 8. Okay, so again, we know that 4 plus 7, again, I know scratch works lots better when we have lots of numbers, but let me just show you what it looks like. 4 plus 7, we said already, is 11. 11 is bigger than 8, so we scratch. How many bigger than 8? 3, so we write down a 3. The question is always how many bigger. That's what we do when we scratch in base 10. How many bigger than 10 is it? Well, it's 3 bigger than 10. It's 5 bigger than 10, whatever the ones digit is. It's how many bigger than 10. And then we carry the number we scratched. We carry 1 because we scratched 1 time. And then we have 1 plus 3 plus 1, which is 5. Again, base 8. So that's what scratch addition would look like. We're going to use the same numbers. We're going to subtract, okay? 3, 4 minus 1, 7, and we will do the standard algorithm first. All right, so here's where this might give you that empathy, Amy, for, did you say it was your nephew? Who's working through this idea of subtracting in base 10. All right, so if we're in base 10 and we borrow how many? 10. So we're going to borrow 8 because we're in base 8. So we can't do 4 minus 7. That doesn't work. So when we borrow from the 8s column, we borrow 8. So the 3 becomes a 2, just like, you know, with ours. That's the same thing. We borrowed one of them. But the 4 actually becomes what? 12. Because we borrowed 8. We borrowed 8. We already had 4. That's 12.
We write it as 12.
We write it as 12. Just like when we're in our number system, when we borrow it, we still write it as 14 or whatever the number is. It's still a 2-digit number in a one-digit column. It's okay. It's not going to be one done. True. But we're turning it into a value that we are going to subtract from. We're turning it into units. Yeah. All right. 12 minus 7 is 5. 2 minus 1 is 1. And this is base, 8. Okay. Let me show you now how equal additions works. What's the purpose and goal behind equal additions? No borrowing. Do not borrow. Do not borrow. Okay, so I can't do the 4 minus the 7, right? So I have to add something here that will turn the 7 into a 0. What do I have to add? 1. That's right. Why do I have to add 1? 7 will turn it into 8, and we have an 8's column, right? But if I add 1 on bottom, I add 1 on top. So 34 becomes 35, or 3-4 becomes 3-5. And then 1-7 becomes, not 1-8, no, 2-0. 2-0, right? I have an 8 in the 1's column, so I have to carry it over, right? An 8's too big in base 8. I don't have any 8's in base 8. So once I get an 8, I have to carry it to the 8's column. And then 3-5 minus 2-0 is 1-5, and we're done. Okay? All right, we'll stop there for today.